Okay, so I think we're ready to get started. So welcome everybody to the July 2020 edition of Space Cafe Tokyo. My name's Ken, I'm one of the co-organizers. Along with me here is another co-organizer, Mayuko. Mayuko, do you want to say hi?
Yeah. Hi everyone. Thank you for joining us tonight.
So as always, you can follow us on social media to find out about our future events. We're on Facebook, Twitter, and Meetup. So please follow these links on the screen right now. So tonight, we're very happy to have Dr. Sadie Jones. She is the Astronomy Public Engagement Leader at the University of Southampton. And today she's going to be telling us about Aurora Quest in search of the Northern Lights. And she also has a Twitter account, so you can follow her. It looks like Twitter, Instagram, and Facebook. So follow her at this hashtag on the screen right now. So if for those of you who it might be your first time following a Space Cafe event, we typically have a monthly event in Tokyo at a bar called Good Heavens in Shimokitazawa. It's a nice venue. Unfortunately, due to the recent pandemic situation, we've moved to online events, but we're still happy to have a lot of exciting speakers from all over the world join us. But hopefully sooner rather than later, we'll be able to get back to doing live events. So before I turn it over to our speaker, just a few rules. So during the presentation, we're going to mute all participants. You can send comments and questions anytime in the chat, whether you're on Zoom or YouTube. For the question and answer session, you can ask questions at any time in the chat box. And then at the end of the talk, we will collect all of those and we will ask them to the speaker, either Mayuko or I. So I think with that, we can probably get started. So I will stop sharing my screen and then Sadie, you can get started.
Okay, hi everyone. I'm going to share my screen now. Okay, can you see this? Just to check, can you see the first slide, Ken?
Yes.
Great. Okay, hi everybody. Thank you so much for inviting me to give this talk. I was in Japan about 2 years ago and I really loved it there. So I wish I was there with you in real life, but these are the times we're in. Yes, so I'm going to talk about this quest that I went on to see the Northern Lights in Norway back in January 2020. So January this year. And my background is that I didn't study space physics. I actually studied the physics of supermassive black holes, but I was invited to go along to this expedition as part of my job, kind of promoting the research of the University of Southampton to a wider public. So I was there documenting every day in a blog, which is called the Aurora Quest Southampton blog, if you wanted to read about what we did on every day in specific detail. But I was also doing social media and like web chats like this one, where we were linking up with schools and showing them what it is like to be a scientist and be in the Arctic Circle in these very extreme conditions. So just a little bit more about me to start you off. So my background is in astrophysics. I did a master's in Cardiff University, which is in Wales, where I'm originally from, in the UK. And then I came to Southampton here in England to do a PhD specifically in supermassive black holes. So in this, if you can see my cursor, hopefully, you can see that in supermassive black holes we have, we believe there is a jet of particles that come out of the center of the galaxy. We don't know how these anchor onto the black holes, and we don't know much about this disk, this called the accretion disk around the black hole. So that was what my PhD was on, and I did that for 4 years. And while doing it, I realized that I really like talking to people about my research. and maybe a little bit more than actually doing the research myself. So luckily for me, the university bought a planetarium, and I've been taking that out into schools for the last 9 years now, and talking about astronomy. I do have a life outside of my job. I've recently started doing something called science comedy, where you're doing stand-up comedy acts about kind of science and the life of a scientist. So that's really fun and scary. And also I play a sport called roller derby, which is again very fun. It's like a full contact sport, which is why I'm wearing a helmet in this photo, with lots of padding, and you're on roller skates. And it's it's a female dominated sport. So it's nice for me, coming from a physics department, which is very male dominated, to have a sport where there's lots of women as well. And during lockdown, I've actually taken up cycling. I have an indoor turbo trainer, which I use. So that's fun. Okay, so today I'm talking about the Northern Lights, or the aurora, specifically the Northern Lights, or the aurora borealis, because obviously that is where the scientists have their camera, which is taking pictures of the aurora. But the aurora does happen in the south. So these are called the Southern Lights, or the aurora australis. But you can only really see these from kind of maybe Tasmania and mainly in Antarctica. So obviously Antarctica doesn't have many people there to observe them. They're basically, when you see them in beautiful pictures like this one, which was taken in Alaska, they're usually kind of green in colour with little tinges of red, and I'll explain a bit more about the colours and how they are produced. But these are essentially just photons of light that are produced high in the Earth's atmosphere. The aurora isn't a static thing, it is moving, it is dynamic, and you can see lots of different features and kind of patterns on big scales as the aurora goes overhead, but also on the very small scales if you zoom in. And that is basically what the scientists at the University of Southampton are trying to do, is they're very interested in this small scale structure and these kind of patterns, because now we have this camera that can look in higher detail than we've been able to look before. You can see the aurora very nicely from space. This is footage from the International Space Station, and you can see as you're looking down on the Earth, you can see these very beautiful kind of rays in green and then red much higher up. So yeah, I wish I could go to the International Space Station and see it this way. That would be amazing. So I've prepared some questions just to kind of get you thinking about the aurora. They're throughout the talk, and I think there is going to be a poll where we can choose one of the 4 answers, but it's just for fun. So I will explain the correct answer. So the first one is, what flies at the same height as the aurora? Is it a bird, a plane, a satellite, or a tennis ball? And I'm not sure if I can see if people are voting, but I'm going to carry on. So have a think about what your answer is. And the correct answer is satellites. So if you look at this diagram here, well, the video I showed you was the International Space Station. So that's at 340 kilometers, and it was obviously looking down on the aurora. The aurora is visible between 100 and 300 kilometers, and the satellites fly at 200 kilometers. So the correct answer was satellites. All the other things I listed were much lower down, like planes and tennis balls down here. So it does take up quite a large kind of proportion of the altitude in our atmosphere, which I guess is why it's so bright and visible. The second question is, where are you most likely to see the aurora? And I'm generally talking here more about the Northern Lights. So the options are Norway, Italy, the North Pole, and Scotland. Sorry that these are so Europe-based. Okay, if you all have a guess, think about what your answer would be. And the correct answer is where you would most likely see it out of these 4 options is actually Norway. So I haven't labeled Norway on the map, but Svalbard, where I went, is part of Norway. And then you have kind of the upper part of Norway here, and then Finnish Lapland and Greenland, Canada, Alaska. So where the aurora is visible is basically where this kind of semicircle is. This is called the aurora oval. So North Pole was thrown in there as like a trick question, basically, because the North Pole is here, and you might think that you would be able to see the aurora there, but because of the way the magnetic field actually comes in and attaches to the Earth, that doesn't happen, and I'll explain that in a diagram later. And then question 3, what causes the aurora? So is it particles from space hitting the atmosphere, the sunlight reflecting off the polar ice caps, ice crystals, or foxes? There is a story about foxes throwing up the snow with their tails into the atmosphere. So have a think about which option you think is correct. And the correct answer is A, particles from space hitting the atmosphere. So in this diagram, you can see we have the sun, which is giving off the solar wind. So it's basically a plasma of protons and electrons, charged particles that are being sent off in all directions from the sun. Now, because the Earth has this, what we call a magnetosphere, it, I guess, protects us from a lot of nasty things in space, which is really good for us as humans. But it means that these charged particles will flow along these field lines and get kind of directed into the Earth. It's not as simple as them just kind of flowing down here and directly into the auroral oval. They actually get trapped in the magnetosphere, which is what this green stuff is showing you. When they get trapped, the plasma is stuck here basically until there is a what we call a reconnection event, and then suddenly all this material flows down onto the auroral oval and allows us to see a very beautiful aurora. This is just another little graphic just to show you the magnetic field lines coming in to the Earth. So the magnetic pole and the geographic pole are not aligned, which is interesting as well. But if you're looking down on the kind of North Pole, down on the Earth, this red semicircle is showing you where you expect to see the aurora, but the actual kind of shape of the auroral oval is very dependent on the amount of plasma and the solar wind and basically what's going on. So this changes very quickly, like, you know, in terms of minutes and hours, this shape will change. And we have, we are also linked with satellites that look down directly on this all the time and will give us a live feed. So when we're in Svalbard in Norway, which is at the very edge of the auroral oval, we can basically look at this diagram and decide whether we're going to see the aurora on that night. So Svalbard is really interesting because it's at the very edge of this auroral oval. So for science purposes, that's what we want to investigate. There is quite a lot of stuff that's done looking kind of in the middle of where this kind of magnetic field is attaching to the Earth, but at the very edge, at the cusp, is why it's interesting and why we have the camera there. Similarly in Lapland, in Finnish Lapland, that is also on the edge, and that is why you get lots of nice displays there. I don't know if you guys do this this experiment in school, but I remember this from my school days, and we had to put iron filings on top of a piece of paper on a bar magnet. And that is just a really nice way of showing you these magnetic field lines. So if you imagine that the Earth has this magnetic, this bar magnet inside it, then it can maybe help you to visualize what is happening and why the North and South Pole get a lot more kind of collection of this plasma right at the poles, rather than kind of, you know, further north or south nearer to the equator. So the sun itself is very well, magnetic as well. It has its own kind of magnetosphere. And this is just showing you some material that's coming out of the sun in these things called prominences. And what happens is these magnetic field lines will kind of snap and then suddenly blast material into space. And I have another image of this. So this is a spacecraft which is again looking at the sun. So the sun itself has been blocked out by this little circle. So this material is all stuff that has been thrown out of the sun, and you'll see a big flare, a big burst of material happen, and then a few seconds later you'll see lots of interference in the actual spacecraft electronics, which will just show you kind of how all these protons and electrons flying around in space is bad for satellites. And obviously this spacecraft would have been designed with this in mind. There you go, you can see all the interference happening there. So yeah, so these flares are coming towards the Earth all the time, and we're generally protected from them by the Earth's magnetosphere. But we still don't really know a lot about the magnetic field of the Earth and that kind of thing. So that's also why we do this type of research. This is just another little video which will show you the way the magnetosphere changes and has these reconnections. So again, you have the sun, obviously, with its solar wind. So the solar wind hits the front end of this magnetosphere, and the field lines are actually, because of the force of this and the fact that this actually has the solar wind has a magnetic field in it, it snaps them back here, and then you have this thing called a reconnection, which then forces this material, this plasma, to suddenly fly down these field lines. And you can see represented in pink, this kind of little crown, if you like, on top of the Earth, is where you're going to see the aurora. Now, if there is a lot of material suddenly kind of injected into the magnetosphere by a big solar wind with lots of material in it, or what we call a coronal mass ejection, then this auroral oval can actually move further south. So people who live like here in the south of England have reported seeing the aurora even from here, because if there's a big storm, this moves down. And I'm assuming this would happen exactly the same in the south. These two shapes, they tend to be symmetrical. So the kind of thing that's happening in the north is also happening in the south. So you might get a situation where they are coming much closer to the equator. Okay, so this is just a few diagrams to show you how it gets the color. We'll mainly see it as green. So these two E's here are representing electrons, charged particles coming from the sun, and these white circles are representing molecules and elements in our air, in the atmosphere of the Earth. So we have lots of oxygen and nitrogen mainly. So as the charged particles hit the oxygen, they basically make the electrons that are within the oxygen itself energized. So the oxygen is excited, let's say, and when the oxygen releases that extra energy it's gained from this electron, it will give out a photon of light. And the photon of light, the color of the photon of light, is dependent on the molecule because of the different energy bands within oxygen and nitrogen, for example. So it just so happens that the oxygen that is more, that there is more oxygen of this type, just O, high in the atmosphere, and this gives off red light, okay? So that is why the International Space Station could see more red. As the electrons kind of come down a bit lower in altitude in the atmosphere, they will hit O+ and nitrogen. And the O+, there is a lot more of it, and then pure oxygen, O2, gives off a green color when it is excited. So there is a lot more well, there isn't necessarily a lot more oxygen, but the oxygen is more easy to excite than the nitrogen, if that makes sense. So that is why you get mainly green aurora, because this oxygen that's a bit lower down is very easy to excite. So you end up with lots of green aurora, and you get what is called a cascade, where these excited oxygen are now also producing charged particles. They're becoming ionized, and you're getting extra electrons, which are meaning that it goes from being quite a faded kind of green color to suddenly being very bright because of this cascade of electrons. When the electrons finally hit a nitrogen and are able to energize it, which is harder for it to do, this is usually a bluey or purple color. So the blue or purple aurora is possible, but it is a lot less. It's a lot more rare. My friend who lives in Finland and had lived there for the first like 20 years of her life, she saw a purple aurora once, and she said it was amazing, but she's only seen it once. Okay, so this is the colors. So you mainly have green and red, and that is, both those colors are to do with the oxygen in the atmosphere. The same thing happens actually when you get lightning. So the reason why lightning is more of a purpley color is because much closer to the Earth, the actual land that we live on, there is a lot more nitrogen. So this lower down, there's more nitrogen. So as the charged particles from the clouds are trying to make their way towards the Earth, they energize the nitrogen as they come down, and that is why lightning looks kind of a purpley color. Okay, so here in the University of Southampton, we don't only investigate aurora in the Earth, we also look at it on planets like Jupiter and Saturn. And this is really cool because they both are very massive planets, obviously, and they have very, very big magnetospheres. And so looking at their aurora from our space telescopes, we'll learn more about those magnetic fields. And there are some more kind of, I guess, crazy theories that planets like exoplanets and planets we find in the future that have aurora are more likely to have alien life because this magnetosphere is kind of protecting the planet. So that's kind of a nice little idea, quite difficult to test, I imagine. Okay, so the expedition I went on in January was to Svalbard, as hopefully you remember, but yeah, so it's part of Norway, but it's actually much further north than Norway. It's very close to the North Pole, but obviously still within this aurora oval. So you have the United Kingdom, where I am now, and then Norway, Sweden and Finland, and then this is still counted as Norway, but then Svalbard is this whole area here. Now, there is only one village of people living on Svalbard, so it's an archipelago, I can never say it. It's a collection of small islands, like Japan, I guess, and everyone who lives there lives in this place called Longyearbyen. So that is where the telescope is that we went to, and that is where everything is, basically. So we flew there. We had 3 different flights to get there. And this is what it looks like in the spring. So I should say that I went with Dr. Dan Whiter, who's been there many, many times before. And he is actually the person who designed the camera that we were working with as part of his PhD many years ago, over 10 years ago. And then his PhD student, David, also came with us. So this is actually a picture that Dan has taken in the springtime when he was there on a previous occasion, because obviously we were there in January, which is winter for Norway. But this is what it would look like. This is the village. You can see lots of houses and things from this view. And this was a picture taken actually from up on the mountain where the camera and the radar is that we were using during the week that we were there. Okay, so based on that knowledge, I have another question for you. How likely do you think is it to be sunny, like you just saw, at midday in December or in January, i.e. the winter, on Svalbard? Okay, so think about that question. So the options are no chance, it's not going to be sunny. 50% of the time it will be sunny. It's always sunny in Svalbard, or 25% likelihood. So have to think about that. Okay, the answer is no chance. So the because of the tilt of the Earth's axis, when Svalbard is in winter time, there is basically no sunlight, which is very, very weird to experience. So while we were there, it looked like this the whole time. So this is a picture taken at midday, at lunchtime, but this is what it looked like all hours of every day. So it's very difficult actually to know when it was day, when it was night. Had no idea what time it was most of the time we were there, because it was in total darkness. And this is just to show you kind of how this works. So because Svalbard is in this area, so in our winter, the northern hemisphere is tilted away from the sun. So it means even as this kind of rotation happens, we're never going to be in a situation where the sun's rays will be able to fall on Svalbard. But then this means obviously in their summer, they have the opposite, where the sun never sets below the horizon. So for a good few months, I think it's about 3 months, they have total sunlight all the time. So they have to use blackout curtains to be able to go to sleep and things like that. And for me, I was quite worried about this. So I actually took one of these SAD lamps to Svalbard, just in case I got a bit depressed from being in the dark all the time. But it was okay, because I was only there for a week. So it wasn't too bad. Okay, so this is just a picture of us. So this is us at the telescope, and we are all ready with our head torches and our buffs, if you like, and hats to go outside. And we were going to start taking the camera out of the telescope kind of protection, because the camera actually was broken and needed to be fixed. And because Dan here is the one that designed it for his PhD, he was obviously the best person for the job. The temperature was about -20 most of the time we were there, which again is much colder than I've ever experienced here in the UK or ever in my life. And it is total darkness, which is obviously why we needed the head torch. Most of the time we would only have these on red, the red light, because obviously we don't want to cause any light pollution to any of the cameras that are taking photos of the aurora. And this is, you can see the radar in the background, which we were also using. So we had a camera, and then there's 2 radars which are aligned exactly along one of the magnetic field lines that comes down into the Earth. Obviously, because we think we will see more activity happening above our heads along those field lines. I'd never seen the aurora before I went on this trip, so this is just me obviously very excited the first night that we had some very bright aurora. And if you've seen pictures of the aurora like this before, you'll think it's very green, but actually some people are quite disappointed because it isn't as green in real life as it looks in photos. It is very impressive, and I found it amazing the way it covers the whole of the sky, and obviously moves quite quickly, but it isn't actually as green as it looks in photos, unless you get a really bright aurora. And I've been told by Dan here, who's been looking for the aurora in many places in Europe at least, that the Finnish Lapland is the best place to see the really, really bright aurora. But for doing our science, Svalbard in Norway was the best place. So this is a picture inside the control room. So this is David, the PhD student. He's just setting up the radar run. So we have the radar running, and at the same time we're ideally taking pictures. But I think for this one of the first radar runs, we didn't have the camera working yet, but we still could take useful images of the radar. So the radar is basically just firing up radio waves into the atmosphere, and then examining how far the radar gets through the aurora, and the radar that is reflected back into the dish tells you kind of about the aurora kind of I guess thickness and things like that. So this one here is the main thing that I understood. A lot of these screens I didn't really understand, to be honest. But this one is showing you a live image from a camera that's looking down on the auroral oval. So you can see exactly where we are in Svalbard, and if we are predicted to have any overhead. So, and then there's also a full screen monitor of what it looks like outside. So if there was some really, really nice aurora that we could take some nice pictures of, then we could run outside. Well, obviously we have to put on like 5 layers first, but run outside after our 5 layers are on and take some nice photos. So this here is one of the nice photos we took. And David used his red head torch to make what we call like a light tag with a long exposure to try and write his name. We also got time to do some ice skating, and it turns out that Dan is actually
presenting Dr. Dan Whiter.
Okay, so you can see that Dan was actually very good at ice skating. He'd been doing some training back here in England before he went. I wasn't very good, and I actually fell over this massive uneven part that's been dug out of the ice. This ice is mainly used for people like playing ice hockey. But the really cool thing about this, again, this was actually taken at midday, so you can see how dark it is in the background. But the really cool thing about this is the most northern ice skating rink in the world. So at this point, Dan was the most northerly ice skater. So that was really cool. Yeah, we spent a lot of time in the radar room. So this is just David taking a well-deserved rest across some seats. And I put this photo in. This was on our flight back, and you can see lots of obviously snow and ice on the runway. And I just thought it was funny because in the UK, at least, if you have any snow on the runway, no planes will fly anywhere. But obviously in Norway, they are very used to this type of thing. Okay, so the question 5, what animal lives in Svalbard? There's actually a few animals, but the main animal that lives there, is it a penguin, flamingo, polar bear, or giraffe? So, well, some of you might already be aware, but there are actually, the answer is a polar bear, and there are actually more polar bears in Svalbard in Norway than there are people. They are a protected species there. You obviously can't kill them or hunt them. And there is loads and loads of polar bears there. But because Svalbard is so big, obviously the hope is that they don't come into Longyearbyen and they stay in their kind of parts of the island. But we did actually have a close encounter with a polar bear while we were there. So this is an image of us. This is like taken from inside the car. So this is kind of like inside the car. And this is the windscreen. And this is a picture of us driving up the mountain towards the radar to start one of our runs. This little light you can see here with a little bit coming out of it, that is a helicopter. So the helicopter is using its searchlight to look for a polar bear. So a polar bear had been, well, people had seen a polar bear that day, and they had warned the government that govern in Svalbard, and they have their own helicopter because this happens so often. So the idea is to try and drive the polar bear out of the village where obviously the people are by kind of just scaring it or kind of blinding it, well, not blinding it, but putting the searchlight on it would hopefully make it run away back to kind of where it was originally from, and away from the people. But to be driving up the mountain in pitch darkness and suddenly see this, knowing that probably means there's a polar bear only a few meters away from the car, it was both exciting and very, very scary. And Dan assures me that this has never happened before. So in the 10 years he's been going back and forth to Norway, there was no polar bear sightings. Like, obviously everyone's very aware that they live on the island, but he'd never actually been this close to one. So I said that I was like a good luck charm, because I was very excited about this. Okay, so polar bears, stuffed polar bears and polar bears on souvenirs is everywhere in Svalbard, because that is their kind of main, obviously, animal. Like, the polar bears are the king of the island. So this is actually not a real polar bear, thankfully. It is a stuffed polar bear that was in a pub, which we took a photo with. But it's just here mainly to show you how big they are. I didn't realize they are actually twice the size of a human. They're really big. Okay, so what happened the next day is that we were up the radar with the engineer, which is called Martin. And Martin had actually left us there on our own because he trusted us to control everything without him. But he sent us this message on Facebook to say basically that the polar bear was back, and that we shouldn't come back down the mountain into the village, because there's these dog parks where they keep all the huskies that drive the sleighs that everyone has. So usually everyone in Svalbard kind of has a dog to pull them on their sleigh, which is also really cool. So because the polar bear had been spotted near the dog park, where I guess the dogs have lots of food, Martin was basically advising us not to drive back down the mountain, because we might encounter the polar bear again. We might be even closer than we were previously. So we left it a few hours before we came back down, and we didn't see the polar bear. And as far as we're aware, the helicopter was able to kind of scare it off, and it went back to where it came from. But it turns out what happened is this man here in the green coat, he was leading some tourists on the sleds driven by the dogs through the valley. And he'd suddenly seen the polar bear. Now everyone who works there and lives there is trained to use a gun, just in case, they need to shoot a polar bear. Unfortunately, if it is a real, danger that everyone is concerned about on the island. But he didn't actually have time, because he was driving or on this ski thing with two tourists on the back, a lady and her daughter. So he actually just kind of punched the polar bear in the nose. And thankfully for him and the rest of the tourists, the polar bear ran away. But yeah, this was all very exciting for me. I don't know how excited I would have been if I actually had come really close to the polar bear, but the story is fun to tell anyway. So this is just to show you, this is taken very seriously. So when Dan first started going to Norway, to Svalbard, he was trained on how to use this flare gun. So he's also trained to use the rifle, but the flare gun is ideally what you would use at first, because it just creates a very loud noise, which would scare the polar bear away. So the idea is that whenever we were going back and forth to the camera, which was outside, we would do a scan with our head torch of the immediate area to see if there was any polar bears. But it is very hard, because obviously polar bears are white and the snow is white. So it was quite scary for those few days where there was, a polar bear around. And they think it was the same polar bear that kept, obviously, I guess, smelling the food somehow. He kept coming back to the town to try and... So I don't know if any of you have read or seen this show, His Dark Materials. It's one of my absolute favorite books. But when I read it as a child, I remember learning about Yorick Bernenson and how he was king of the bears on Svalbard. And I remember thinking that Svalbard was a fictional place. So it was really, really cool for me to go there and realize that it was obviously a real place and that there were real polar bears there. So yeah, I felt like Lyra, who is the kind of heroine of the story. Just to show you again what this this kind of looks like when it isn't pitch dark. This is the road that goes up to the radar, which when it's in this kind of summer or springtime, you can see it all looks very nice. And of course, there is a danger sign just warning you to be aware of the polar bears. And the science station, which we're trying to get to, is up here. This is what it looked more like when we were there. Lots of snow, and again, the sign. This didn't happen when I was there, but they have, if there's a lot of snow, a big snow drift, then they've had to kind of get towed or you know, so try and get their car out of all the snow. But luckily that didn't happen while we were there. So the place where we're going on top of the mountain is to these radars. And luckily for us, the road all the way up to the radars is nicely ploughed. And that is because there is a coal mine on the mountain, so that all the village is powered by coal. And to get the coal back and forth, obviously they need big trucks, so they need to plough the road very often. So that's very good for us as scientists, because it means we don't have to worry about paying extra money to plough that road that goes up to the dishes. Just in case you're wondering, these two dishes are represented here in terms of how many polar bears you could get across them. So the really big dish, which is 15 polar bears across, is always pointing up in one direction. And then this one, which is a bit smaller, is steerable. So we can actually point it at a certain part of the aurora if something exciting is happening. And this is just to show you again that people are much smaller than polar bears. So the camera here is up on a shelf on the side of the building, and then the two radars at either side. And then the actual village where most of the people are in this valley here. And this is the road that we came up every day to do our radar runs. Okay, so the University of Southampton has this camera, which I spoke about, which is called ASK, which means Aurora Structure and Kinetics. And it's doing exactly that. It's looking for how the aurora moves and the small scale structure that you can see within it. Okay, so that's basically what we're trying to do. And just a little aside is that this ladder is held on by a rope. So every time we need to go up to the camera to kind of fix it or move it during our repair, we had to go up this ladder, which was a bit scary as well. But the one time I was coming down the ladder, there was suddenly a light on me, and I thought that it was a helicopter and that there was a polar bear at the bottom of the ladder. So I quickly ran back up the ladder and then realized that it was just a car with its headlights on coming down the road. So yeah, it was very scary for a few minutes, but thankfully it wasn't the polar bear. There is another device we used, which is a spectrograph, which is at the observatory, which is further up the mountain. But unfortunately, it's further up than the coal mine. So to get to it, we had to go in this tank, which was apparently borrowed from the Norwegian army, or gifted to the university, so they could go up and down the mountain. So that was really fun as well. Very loud, but fun. Okay, so the spectrograph is, again, it's just similar to the camera, but it's looking at individual elements that can be seen in the atmosphere above the camera. But the ASK camera, if this is a picture of you looking up from Svalbard at the whole sky, it is only looking at this very small area here, which is aligned along a magnetic field line. And you will see kind of like a little short video clip of the aurora that's happening in that region in the three RGB colors using the three cameras, basically. So what we're doing as scientists is trying to compare or combine the optical information from the camera, the spectrograph, the radar all together. And this will allow us actually to model the changes in temperatures at different heights in the atmosphere. My final question is not really part of the poll, but it's just to make you aware that the aurora research is important and you should care about it. But one of the main reasons, which I didn't realize till I started working with the space scientists, is that the altitude of where you see the aurora, it is considered by people who are interested in meteorology and, you know, Earth weather. So basically, the aurora dumps a lot of energy into the atmosphere. So it is quite a minimal effect, but it does affect our weather. So it can be kind of partly responsible for weather systems and storms. And also because it is at the same altitude as the satellites, it can also have an effect on them. So satellites need to be kind of prepared for the fact they may get a lot of interference. Okay, so with the camera, it has been taking data for 12 years. So we have lots and lots of images of the aurora, but even with our PhD students, we don't have enough time to analyze them all. So we've created this thing called the aurorazoo.org website, where we've uploaded lots of pictures and images, and basically we need help, and anyone is able to just look at these pictures and decide what shape they think they are just by looking with their eyes. And by helping us, you will be contributing to actual real research into aurora that's never been done before, because nobody's actually looked this closely at the aurora before. So just to finish up, I'll just skip through this question because this is kind of a trick question. But if you do go onto the aurorazoo.org website, please do, you'll see that it will ask you different questions about these images from the ASK camera that you're seeing, and you will be able to help us classify the shape. So is it an arc? Is it a ray? Can you see aurora everywhere, or is it very kind of irregular? And also what kind of motion it has. So these two here, chocolate sauce and psychedelic kaleidoscope, are actually classification for the motion of the aurora that have actually been named by PhD students for what they think these most look like. So they thought this looked like milk and chocolate sauce swirling around in a cup, I guess. But yeah, these names will actually hopefully soon go into actual academic papers, and it'll be the first study that recognizes this kind of structure. And there's other questions that are asked on there. So yeah, if you would be interested in going on to the Aurora Zoo website, you'll be met with a screen like this. And basically, if you just press this play button, you'll see the little mini video of the aurora that you're being asked to classify. And you just click these buttons to tell, to decide which kind of shape you think it is. But there isn't really a wrong answer because it's all based on statistics. So it's not just you that will be asked to look at this one video. There'll be other people who are asked to look at it, and it's kind of based on what most people think. Final thing to say is that the Aurora Zoo is actually part of a very big citizen science project called the Zooniverse. So if you go onto the zooniverse.com and register yourself as a user, you'll see there's loads and loads of other scientists who have data on there that they need help analyzing. So I've got quite addicted to one that's about penguins and counting penguins in Antarctica. There's other ones about planets, finding planets that might have, stars that have planets, exoplanets on. So you can try and see if you can get loads and loads of classifications, more than your friends, at least. So that's the end. Thank you very much for listening, and hopefully we'll have some questions.
All right. Thank you, Sadie, for a wonderful talk. So we will move to the question and answer session now. So we will go to YouTube for a few questions. So the first question is, if there is aurora activity on exoplanets which have different composition atmosphere, the colors should also be different, right?
Yeah, exactly. So if they have different atmosphere, their aurora will be different colors. So yeah, for example, if they had nitrogen, they would have mainly purple aurora. So yeah, that would be a good way of us learning what composition the atmosphere is and maybe what the aliens would look like. But we can do that kind of thing with spectrographs as well. So if we look at the light, not the light from the planet obviously directly, but the reflected light from its star can tell us what atmosphere the planet has. But it is obviously very difficult to predict, because life could evolve in any kind of situation, right? So even if you know it has a atmosphere very different to us, it doesn't mean there isn't any aliens. And if it is very similar to us, it doesn't mean that there are humans there.
Okay, so the next question is, in the total darkness, do people still wake up in the morning and go to bed at night?
Yeah, that's a good question. Yeah, I mean, everyone tries to keep as much kind of a normal day where you're still going to bed, and trying to get as much sleep as possible. But yeah, you all still wake up in the morning and you go to bed at night. It's just very weird to call it the morning when it's, when it's still pitch black, and it does affect you. And I don't think, to be honest, I could live there, because a lot of the scientists who we worked with, they live there all the time, right? But they said that in the summer, when it's sunny all the time, is actually worse, because you feel like that you should always be outside doing stuff because it's sunny. So they struggle more with not wanting to be out enjoying the sun, especially when they know that 3 months of darkness is coming.
Okay, so I actually have a question. Can you say anything about the difference between the northern lights and the southern lights, aside from obviously the location?
There is another scientist I work with who is, they use two spacecraft which are looking at the northern and southern lights simultaneously all the time. And the interesting thing, I think, the most interesting thing to come from that research is that they do look very similar. So the structures and shapes you see. So if you were in the south and I was in the north, and we're both looking at the aurora, the features we would see, well, on the bigger scales anyway, are similar, like almost the same. And that's just to do with the fact that when the material comes into the magnetosphere, it is kind of equally distributed to the north and the south. So you wouldn't have like really, really bright stuff happening in the north and then nothing in the south. It's kind of always the same because of the amount of material that comes in. But yeah, there is a lot less footage and research done of the southern lights because of Antarctica being more difficult for people to live on and get to and things like that.
Okay, I think that's all the questions we have.
Can I ask a question?
Oh yeah, sure.
Sorry. So I just missed, but what kind of physical process caused the difference of the shape of those aurora, like psychedelic or something?
Yeah, I mean, that's basically the question of the research. We don't really know. They think it's to do with the different layers of material, like as you go up through the atmosphere, and the different temperatures. So that's what David, who's the PhD student, that is basically his research to find out the temperature differences as you go through like a section of the aurora in different heights. And that will hopefully feed into weather research that is done on the Earth to see if the aurora, when there is really bright aurora with lots of energy, does that mean we have different types of weather, or we have more hotter weather in that kind of area as well?
Yeah, thank you.
So we actually have one final question that just came in from YouTube. The question is, is it possible the aurora's altitude changes in some degree? What would happen if the altitude changes below 100 kilometers above the Earth?
So I don't think the aurora would be visible below 100 kilometers, but that's just to do with like the chemical composition. So like the lower down you get, just due to gravity and how heavy different elements are, there is a lot more nitrogen, and the nitrogen is much harder to energize via the charged particles from the sun. So the charged particles from the sun come in, and most of them have already energized things higher up. So by the time they get to the lower down altitudes, there isn't enough energy to make the aurora happen. But the aurora can be seen at lower altitudes on the Earth, if that makes sense. So it can actually come down lower so that you can see it in countries closer to the equator.
Okay, we actually got a final question that just came in on YouTube. Okay. Okay. I've heard that Jupiter's magnetic field is heavily affected by the existence of its satellites, and then in parentheses, only Europa, question mark. Are there any effects of satellites on Jupiter's aurora?
Not that I know of, actually, but there is a PhD student who is working on Jupiter specifically, who I'm sure would know the answer to that. But sadly, I don't actually know.
Okay, maybe if you can send that info in the chat, we can paste that in the YouTube chat at some point.
Okay, I can do that.
Okay, so I think that'll conclude the question and answer session. So, so thank you again, Sadie, for the wonderful talk.
Thank you very much for having me.
Can you stop screen sharing, and I will share the final announcement slides?
If I can, how to do that? Oh yeah, got it. Ah, sorry, my mouse keeps disappearing. Sorry, it's really weird, like my mouse disappears. Hang on.
Okay, let's see, this works. Okay, do you see the announcement slides? Okay, I think it's working. Okay, so once again, I'll show Dr. Sadie Jones's social media information here on this slide. So follow her on Instagram, Twitter, or Facebook. So just a few final announcements before we close. So normally when we do this event live at in Shimokitazawa at Good Heavens Bar, we have a ticket system where people will pay for a ticket to get in, and then they can get a drink and all that. Obviously, with moving to an online system, everything is free, so nobody has to pay anything, which is nice. But if you're so inclined, we would appreciate if you would contribute a donation to the International Astronomical Union. So the IAU does a lot of work beyond just the scientific astronomy work. They do a lot of outreach, and they contribute a lot to education and society. So if you're so inclined, please visit iau.org/donate and give a donation to the IAU. Our friends over at Tokyo Nerd Night have been putting on online events as well for the last few months. They also do one event per month on a much more broad set of topics, but it's fairly similar type of event. My understanding is that they are taking a break in August, so their next event will be in September 2020. So please check them out at either this website or the social media links on the screen. And just a reminder, so that you can find out about our future events, please follow us on social media. So we are on Facebook and Twitter at these links. And we also have 2 meetup groups, one of which we share with Nerd Night, the other which is our own. You can check them out at these links here. And just a quick acknowledgement of the Space Cafe Tokyo team. So I'm Ken. Mayuko was here helping me today. We also have Tilina, who is another one of the main co-organizers. Ayako runs the Japanese language version of Space Cafe Tokyo. I think they will be starting up their events again, hopefully sometime in the next month or so. And Michelle, our photographer. And as far as our next event, we are still working on that. We have a potential speaker, but we will announce the details, the date, and it's going to be another online event in August. So we will make the announcement through our social media channels. So once again, thanks, Sadie, for the wonderful talk, and we'll see you next month.